The universe is in constant motion, with galaxies drifting, colliding and expanding away from one another due to the relentless force of cosmic expansion. However, scientists have discovered something strange. Our Milky Way, along with hundreds of thousands of other galaxies, is being pulled toward an immense, unseen force at over 600 kilometers per second. This gravitational anomaly, known as the Great Attractor, remains one of the most perplexing mysteries in astrophysics. Located roughly 150 to 250 million light-years away, the Great Attractor exerts an overwhelming gravitational influence on the entire Laniakea Supercluster, a vast collection of galaxies that includes our own. Yet, despite its massive pull, it remains hidden from direct observation, lying in a region of space obscured by the Milky Way's dense stars and cosmic dust, an area known as the Zone of Avoidance. For decades, astronomers have struggled to understand what exactly the Great Attractor is. Is it a gigantic cluster of galaxies, a hidden superstructure of dark matter? Or is it part of an even larger gravitational force shaping the cosmos? As new telescopes and observational techniques push the boundaries of what we can see, we are beginning to uncover clues about this invisible force and its role in the large-scale structure of the universe. Yet the Great Attractor remains an enigma, raising profound questions about the hidden forces guiding the motion of galaxies and the true nature of cosmic gravity. In the 1970s and 1980s, astronomers studying the motion of galaxies noticed an unexplained drift. Our Milky Way, along with the entire local group of galaxies, was moving toward a specific region of space at an extraordinary speed of 600 kilometers per second. This was unexpected because the universe is supposed to be expanding outward due to the Big Bang, with galaxies moving away from each other. Yet something was pulling us inward with immense force. Scientists initially assumed that this motion was caused by the Virgo Supercluster, a massive collection of galaxies about 65 million light-years away. However, as more data became available, it became clear that the pull was coming from a much larger, more distant and unseen structure. In 1986, astronomers R. Brent Tully and Richard Fisher coined the term Great Attractor, referring to this powerful but hidden gravitational anomaly that seemed to be influencing the motion of entire galactic clusters. What made the Great Attractor even more puzzling was that it lay in a part of the sky known as the Zone of Avoidance, an area heavily obscured by the Milky Way's thick clouds of gas, dust and stars. This made direct observations nearly impossible with traditional optical telescopes, leaving astronomers to rely on indirect methods such as radio waves, X-ray observations, and galaxy velocity measurements to detect what was lurking beyond. As technology improved, astronomers were able to map out more of the large-scale structure of the universe, revealing that the Great Attractor was part of a much larger cosmic network of galaxies. The forces at play seemed to extend beyond what was initially expected, suggesting that the Great Attractor might not be a single massive object, but rather a gravitational effect caused by a vast, interconnected web of galaxy clusters, superclusters, and possibly even dark matter. Yet, despite these discoveries, the true nature of the Great Attractor remains one of the greatest unsolved mysteries in cosmology. One of the biggest challenges in studying the Great Attractor is that it lies deep within the Zone of Avoidance, a region of space where thick cosmic dust and the overwhelming brightness of the Milky Way obscure our view. This zone, which covers about 20% of the sky, has long acted as a cosmic blind spot, making it incredibly difficult for astronomers to observe what lies beyond our galaxy. For decades, this region remained almost completely unexplored, leaving the Great Attractor shrouded in mystery. Traditional optical telescopes, which rely on visible light, struggle to see past the dense gas and dust of the Milky Way. However, modern astronomical techniques have allowed scientists to peer through this cosmic fog. Radio telescopes, which detect radio waves unaffected by dust, have helped map galaxies hidden behind the Zone of Avoidance. Likewise, X-ray telescopes, such as NASA's Chandra X-ray Observatory and ESA's XMMM Newton, have revealed hot gas and galaxy clusters beyond our immediate line of sight. Through these advanced observations, astronomers have uncovered massive structures beyond the Milky Way, including the Norma Cluster, a dense collection of galaxies thought to be a major component of the Great Attractor. Despite these findings, the full extent of the Great Attractor's influence remains unclear. Some scientists suspect that it is just one part of an even larger gravitational force, one that spans across hundreds of millions of light-years and extends beyond our current observational limits. This limitation highlights one of the greatest challenges in cosmology: understanding the large-scale structure of the universe when key regions remain hidden from view. While new technology continues to improve our ability to see into the Zone of Avoidance, much of the Great Attractor's true nature is still locked away behind a veil of cosmic dust, leaving us with more questions than answers. One of the most promising tools in this quest is the use of infrared and radio telescopes, which can peer through the dense gas and dust of the Milky Way to detect galaxies hidden in the obscured regions. The 2-micron All-Sky Survey, 2MASS, and the Parkes High Zone of Avoidance Survey have already revealed thousands of previously unseen galaxies in the direction of the Great Attractor, helping to map the hidden structures exerting gravitational influence. Additionally, next-generation observatories such as the Vera C. Rubin Observatory and the James Webb Space Telescope, JWST, are expected to provide even deeper insights into cosmic structures. These advanced telescopes will allow astronomers to probe the universe with unprecedented detail, offering new opportunities to refine our understanding of how superclusters like Laniakea and Shapley interact on cosmic scales. Another frontier in this research is the role of dark matter and dark energy in shaping large-scale cosmic flows. While we now have a clearer picture of how galaxies move under the influence of gravity, the nature of the unseen forces at play remains one of the greatest unsolved mysteries in physics. Some researchers propose that vast halos of dark matter may be guiding the motion of superclusters, while others suggest that dark energy's repulsive force could be counteracting some of the gravitational pull. As our observational capabilities continue to improve, we may one day unlock the true nature of the forces driving our galaxy's motion through the universe. Whether the Great Attractor is merely a stepping stone to an even larger discovery or a key piece of the cosmic puzzle, it remains one of the most fascinating and enduring mysteries in astrophysics. The more we learn about this immense gravitational force, the closer we come to answering one of the biggest questions in cosmology. What is truly shaping the destiny of our universe? Despite the progress we've made in understanding the Great Attractor, many unanswered questions remain. One of the most profound is whether our galaxy's motion is part of a much larger cosmic dance. A chain reaction of gravitational influences stretching across billions of light years. The discovery of the Shapley Supercluster and other massive structures beyond the Great Attractor suggests that what we once thought was the dominant force may be just one piece of an even grander cosmic puzzle. Some scientists speculate that even larger unseen structures, such as the Sloan Great Wall or the Hercules Corona Borealis Great Wall, may exert influence over our supercluster. These colossal formations, spanning billions of light years, represent some of the largest known structures in the universe. Another intriguing possibility lies in the nature of cosmic voids, vast empty regions of space with very few galaxies. While the Great Attractor is a gravitational well, there are also large repelling forces, such as the dipole repeller, which seem to push galaxies away. Ultimately, as we continue to refine our understanding of the universe's large-scale structure, we may find that our galaxy's journey is not random, but part of a vast interconnected web of gravitational interactions, stretching beyond our observational limits. Whether the Great Attractor is a key player in this motion, or merely a waypoint in a much grander cosmic migration, remains to be seen. However, one thing is certain. Our place in the universe is far from static, and the forces shaping our galaxy's future are far more mysterious than we ever imagined. The search for answers about the Great Attractor is far from over. As astronomers continue mapping the large-scale structure of the universe, they are uncovering deeper complexities in how galaxies, dark matter, and gravity interact on cosmic scales. Future discoveries may reshape our understanding of not only the Great Attractor, but also the fundamental nature of the universe itself. One of the biggest challenges in studying this phenomenon is our own location within the Milky Way. The Zone of Avoidance, the region of space obscured by our galaxy's dense gas and dust, still hides a significant portion of the structures influencing our motion. However, upcoming infrared and radio surveys, along with the data from space telescopes, are expected to reveal more hidden galaxies and structures, bringing us closer to a complete map of the forces acting on our supercluster. Another exciting avenue of research involves the role of dark matter. While we can see galaxies moving toward the Great Attractor, much of the mass responsible for this gravitational pull may be invisible. If dark matter is concentrated in vast, unseen halos surrounding these structures, it could explain the enormous attraction we observe. Additionally, the mysterious force of dark energy complicates our understanding of large-scale motion. How these two competing forces interact on supercluster scales is still not fully understood. Could dark energy be influencing the flow of matter toward the Great Attractor in unexpected ways? Some scientists propose that the expansion of the universe may eventually overpower these gravitational flows, preventing future mergers of superclusters. With the advancement of telescope technology and computational simulations, we are getting closer to answering these profound questions. The Great Attractor, once thought to be a single dominant force, is now understood as part of a much larger and more intricate cosmic network. Whether it is merely a stepping stone to even greater discoveries or a key puzzle piece in understanding the fate of our galaxy, its influence is undeniable. The more we uncover, the more we realize that our universe is a place of unimaginable complexity and wonder, and our journey through the cosmos is far from over. The study of the Great Attractor is a testament to the ever-evolving nature of astrophysics. Every new discovery opens the door to deeper mysteries, revealing that our universe is more complex than we ever imagined. While we have uncovered much about the forces guiding our galaxy's motion, there is still so much left to learn. As we refine our cosmic maps and uncover hidden structures beyond the Zone of Avoidance, we may one day pinpoint the exact source of the Great Attractor's influence. Whether it is a dense cluster of dark matter, an intersection of cosmic filaments, or just one link in a chain of even greater gravitational forces, the true nature of what is pulling our galaxy remains an open question. In the grand scheme of the cosmos, Our galaxy is a mere traveler in a vast and dynamic universe, moving along gravitational highways that stretch across unimaginable distances. The Great Attractor is just one stop on this journey, a powerful reminder that our place in the universe is shaped by forces far beyond our everyday experience. As we continue to explore, map and theorize, we edge closer to unraveling the grand design of the cosmos, revealing not only where we are going, but also the intricate web that connects everything in existence. The quest to understand the Great Attractor is not just about mapping our galaxy's movement. It is about uncovering the hidden structure of the universe itself. The more we learn about this vast cosmic influence, the more we realize that the universe is far more interconnected than we ever imagined. Every new discovery challenges our assumptions. While the Great Attractor once seemed like the dominant force in our region of space, we now know that it is part of an even larger gravitational network, with structures like the Shapley Supercluster exerting an even greater pull. The concept of a static universe has long been discarded. Instead, we exist in a dynamic, ever-evolving cosmic landscape where galaxies flow along vast rivers of gravity drawn toward massive, unseen forces. Yet, even with all we have uncovered, we are still faced with more questions than answers. How does dark matter influence these movements? How does dark energy counteract gravitational pull on cosmic scales? And what lies beyond our current observational limits? Could there be even greater attractors guiding the fate of entire superclusters? With every advancement in technology, from deep space telescopes to powerful computational simulations, we come closer to answering these questions. But the most profound realization may be this: our universe is not just expanding, it is alive with unseen forces, intricate connections, and endless mysteries waiting to be uncovered.